Hello students, in this video we'll see examples of how to convert standard distributions into distributions of the linear exponential family. So recall that if we have a normal random variable, normal with mean mu and variance sigma squared, then its PDF is 1 over the square root of 2 pi sigma squared, e to the negative, and we'll let y be our variable this time, y minus mu squared over 2 sigma squared. And so what we'll do is we'll write this in terms of an exponential only. We'll write this as exponential of, let's expand this out. We'll have a negative y squared over 2 sigma squared. We'll have a positive 2y mu over 2 sigma squared. We'll have a negative mu squared over sigma squared with the 2. And then we'll have a natural log of the square root of 2 pi sigma squared. So I put everything in the normal distribution into a single exponent. And so now I want to isolate the term that just has a y in it. So what we'll do over here is we'll write this as the exponential of a y times 2 mu. So we'll write this as a y times mu over sigma squared. And I'll write this as a minus mu squared over 2. And then we have this extra term over here, so we're going to group that term over there. So we have the plus natural log of the square root of 2 pi sigma squared, and then a minus y squared over 2 sigma squared. So we just algebraically manipulate the form of the PDF of a normal random variable into this form. And so what we can see now is we can see that if we make a conversion where mu is equal to theta, this will become, and then we'll write b of theta as, well, if my mu is theta, this is going to be a negative theta squared over 2, so it's going to be a theta squared over 2. And if I let my phi be equal to sigma squared, and my a of y phi to be equal to the natural log of the square root of 2 pi sigma squared minus y squared over 2 sigma squared. Under this transformation, what we see is it becomes the exponential of y times theta minus b of theta, that's theta squared over 2, over phi, plus this whole thing over here I'm calling a of y phi. So we've shown that our normal mu sigma squared random variable can be put into the form of a linear exponential family. And so let's verify this. So if we look at this, we know that our b prime, so what is our expected value? Our expected value of a random variable, let's call this random variable over here y. Our expected value of y, our formula for this, is b prime of theta. Well, b prime of theta is going to be what? The derivative of theta squared over 2 is just going to be theta, and we know that theta is equal to mu, so that checks out. We know that the variance of y is phi b double prime of y for a linear exponential family, so this is going to be sigma squared. The second derivative of b is equal to 1. So indeed it checks out, and we have written our normal random variable in the linear exponential family. Let's see that a discrete distribution can also be put into the linear exponential family. Let's consider the Poisson distribution, Poisson lambda. So we have a Poisson lambda distribution. And so of course, what's the PDF of a Poisson lambda? It'll be lambda to the y, and then I have an e to the negative lambda over y factorial. And of course here the support of y is equal to 0, 1, 2, 3, etc. So what we'll do is we'll take this lambda to the y, e to the negative y over y factorial, and write this as e to the negative lambda plus y log of lambda, and then minus the log of y factorial. And so what we have over here is, if we simplify this, we're going to have exponential of y times the log of lambda minus lambda. I'll put over 1 over here. And then I'll put a minus the natural log of y. So minus natural log of y over here. And now what I'll do is I'll make our transformation to turn this into linear exponential. What I'll do is I will let our theta over here, let's let theta be the natural log of lambda. So lambda is equal to e to the theta. And what we'll have over here, so that tells us that this over here, this lambda is going to turn into my b of theta, and this over here will be my theta. My phi will be equal to 1. We'll set phi equal to 1. And then my a of y phi will be negative natural log of y factorial. And so if this is the case, then what we see is that we have expression in the form exponential of y times theta minus b of theta over 1 plus a of y phi. My phi is equal to 1. And let's check. So we know that what will our b be? So our b of theta is lambda, and lambda is e to the theta. So b of theta is going to be e to the theta. And so what's b prime of theta? B prime of theta is just going to be e to the theta, and that's equal to lambda. And indeed, we know that the mean of a Poisson is lambda. Let's do the variance. B double prime of theta times phi is 1 times e to the theta, which is also equal to lambda. And so the variance of a Poisson is lambda, and that checks out with what we know. We know that if you have a Poisson lambda distribution, its mean and variance are both equal to the parameter lambda. So if we're given a probability distribution, like a normal or a Poisson, we can put it into the linear exponential family. You can show that gamma distributions are also in the linear exponential family. Binomial random variables are also in the linear exponential family. So traditional, typical random variables that we've seen in our probability course can be put into this linear exponential family. If, however, there is a random variable where the support of the random variable is changing based on a parameter, we cannot put that into the linear exponential family. Thank you very much.